In this video, I'm going to discuss the conjugate acid and the idea that conjugate acids and bases, which is probably the most confusing part of Chapter 9. So I'm going to start by discussing the Bronsted-Lowry theory of acids and bases. There's a lot of ways we can define acids and bases. This is my preferred way. In any case, a Bronsted-Lowry acid is a substance that can donate a proton to another substance, or you can also refer to a proton as an H+ ion. Keep in mind, hydrogen is just a proton and electron. When it becomes an ion, it loses that electron and just becomes a proton. So we can refer to an H+ ion as a proton. Same thing. All right, so a Bronsted-Lowry base is a substance that can accept that proton. But keep in mind, an acid cannot donate a proton unless a base is around to accept it. But H+ ions do not exist by themselves in solution. They're going to react with water to form hydronium ions. So we have this H+ plus water. You'll notice water has the lone pairs here on the oxygen. And it'll form H3O+, where that bond between the proton and one of the lone pairs on the oxygen atom is a coordinate covalent bond, where the oxygen is supplying both electrons to the bond. So here's an example of a Bronsted-Lowry acid-base reaction. We have water. In the first one, water plus HCl making hydronium ion plus chlorine ion. Here, HCl is my acid. It's donating a proton to water, which accepts it to form hydronium plus chlorine ions. My second example, I've got ammonia plus HCl reacting to form ammonium ion and chlorine ion. Here, HCl is again my acid, is donated a proton to ammonia, which is my Bronsted-Lowry base, to form NH4+, and then Cl-. So Bronsted-Lowry acids must have at least one hydrogen atom to donate, and Bronsted-Lowry bases must have at least one non-bonding pair of electrons to accept that proton. Now, when we have conjugate acid-base pairs, that's when we have pairs of chemical species where their only difference between the pair is an H+ ion. So let's look at this example of HF reacting with water to make hydronium ion and F-. Here I have two conjugate acid-base pairs. I've got the HF and F as a conjugate acid-base pair, where the only difference between HF and F- is that proton, the H+ ion. My other conjugate pair in this reaction is water and hydronium ion. Here, H3O+ is my conjugate acid, and water is the conjugate base.